Barton deoxygenation. The Barton-McCombie deoxygenation is an organic reaction in which a hydroxy functional group is in sorry a hydroxy functional group in an organic compound is replaced by a hydrogen to give an alkyl group. It is named after British chemist Sir Derek Harold Richard Barton, oh large name, and Stuart W. McCombie. This deoxygenation reaction is a radical substitution. I have shown this mechanism here. At first take an alcohol and treat it with a base. So the base will take up this proton and then you will get alkoxide ion. This alkoxide will attack this carbon disulfide CS2 and will form this structure. This sulfur anion will take up a methyl group from the methyl iodide and ultimately it will form a xanthate. Now come to the structure of AIBN, that means azo-base isobutylonitrile. This is the structure of AIBN and this is the radical initiator. Let me zoom in. This is actually the radical initiator. This bond this bond and this bond goes through a homolytic cleavage. That means this and this. These two bonds goes through a homolytic cleavage, thus a radical is formed. This one radical. This is the 2-cyanoprop-2-il radical. And this will form nitrogen. After that, this radical will take a proton from this Bu3SNH. I have to zoom this. And then this Bu3SN radical will attack this sulfur. And this bond will be opened and this carbon will become a radical now. Now after that, this radical will go here and this bond will be broken. So ultimately an alkyl radical will be formed. And this alkyl radical will snatch a hydrogen from Bu3SNH and ultimately it will make an alkane from an alcohol. The reaction mechanism consists of a catalytic radical initiation step and a propagation step. The alcohol is first converted into a reactive thionoester or xanthate. Heating of AIBN results in its homolytic cleavage, generating two 2-cyanoprop-2-il radicals which abstract a proton from tributylstannone to generate tributylstenyl radicals. The tributyltene radical attacks the xanthate group at the sulfur atom, which leads to a homolytic cleavage of the CS pi bond. This leaves a carbon-centered radical that forms a CO pi bond through homolytic cleavage of the RO sigma bond, giving rise to an alkyl radical. The sulfur-tene bond in this compound is very stable and provides the driving force of this reaction. The alkyl radical then abstracts a hydrogen atom from another molecule of tributylstannone, generating the desired deoxygenated product. Now a new radical species is ready for propagation of the reaction. This is another mechanism which I have shown. If you wish, you can just do this yourself. First take this glucose, then react it with acetic anhydride, then you will get pentacetate, and then react it with HBr. Oh, react it with HBr. Then this bromine will take the axial position, and then from this, if you give zinc, this zinc will snatch this bromine and form a glycol. After that, I think I have missed something. Okay, I have missed this OAC groups. OAC and OAC will be here. This will form a glycol. And if you react the tributyl stannone here and this double bond CN, if you react here with this, then you will get actually this one. Now I am telling you the mechanism. At first, this radical will snatch a hydrogen from this. This will snatch a hydrogen. Then this will become a radical. Then this radical will attack the bromine. After that, the bromine will give its electron here. Actually, this bonded electron, one electron will be taken by bromine, another one will be taken by this carbon. So a radical, carbon radical will form, and this radical actually attacks here, and then this species will be formed, and at last this will snatch a proton from this, and ultimately the product will be formed. Now just this is an important note about glycals. What is glycal? Actually, glycals are sugar derivatives which have a pyranose ring structure and a double bond between C1 and C2. For example, D-glucal. Glycals may be prepared by reducing acetobromo compounds with zinc dust and acetic acid. So this is the form of glycal, where this C1 and C2 carbons are attached with a double bond. Okay.